Students, in the last class we have to discuss the one criteria of the subgroup. We have to just check a subset H is a subgroup if H is a non-empty and H is a closed and every element has a inverse is also belongs to the H. If these three conditions hold, we can say that H is a subgroup. So we have to discuss in the last class is a one example, and then now we have to start today lecture is also another example for this one more example of this set, and we have to just say that this is not a group under the, suppose we have to begin with the Z10 under modulo 10 is not a group under the multiplication of a modulo 10. So this group Z10 clearly Z under multiplication modulo 10 is not a group because is clearly Z10 and is a closed under the multiplication modulo 10, and also you can see identity 1 is also belongs to there, but not every element has a inverse is there. So Z10 is not a group with respect to the multiplication of modulo 10 since some of its elements do not have a inverse. For example, it is easy to show that 4x is equal to 1 has a no solution of a Z10. So we if you remember, we have to just say that this under multiplication is this is only satisfy the inverses exists only when this set element of A and N are relatively prime. So here we just say that for example I take a 4, so 4 GCD of a 4 is 4 and 10 is equal to 2. So this is 4 and 10 are not a relatively prime. So as also we have to just say that 2 and 10 is also not a relatively other elements is also not a relatively primes is there. So clearly we can say that 4 and 10 is equal to GCD is equal to 2 is not equal to 1. So we can know when this is clearly this is set Z10 under multiplication modulo 10 is not a group because the inverse does not exist in this case. Now it is very analyze we have to taking a because you know that Z10 under we have two element of this types 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we have to and so on like this. We have to just say that is this form. So so we just say that if we take any subset of this 2, 4, 6 and 8, then clearly this H is a subset of this clearly this H is a subset of Z10. Now we see this subset of Z10. You can see this clearly. This is table by this table. Now we have to interesting into these two. We can see clearly this table you have to just check is a closed because every element of a this table are the element of a H, and also you see this identity element is a 6. E is equal to 6 as the identity element of this thing, and you can see the inverse of this is equal to every element of this has a inverse also, but we can say that so this clearly form this H surprisingly that the table reveals that 6 has served as a identity element of H, and H is actually constitute a group under the multiplication modulo 10. However, it is important note that it is not a subgroup of Z10 as Z10 is not a group under multiplication. This subset clearly satisfy all the properties of this group property we have to taking in this form, but we cannot say this H is a subgroup of a G because the first we say that let G be a group, then a subset of this G is a group if it's the same binary operation is a group. But in this case, our case, actually G is not a group, but we have to take some subset, and that subset is a form all the properties of a group satisfy these conditions, and we say that these are the group, but no, it's not is a subgroup is there. Why is not a subgroup? Because the original G is not a group and under this binary operations. So that means we have to this thing very keep in mind. The first we have a G is a group, then only subset is satisfied, is a subset, and this subset is itself is a group, then we have to say that this H is a subgroup of a group G. We have to, in the last lecture I just said that in the end, okay, we have to reduce this condition, 3 conditions to like as a 2, or we have to just say that 1. That's a condition criteria is called is a equivalent set of conditions for a subgroup. In this we say that let G be a group and H a subset of a G, then H is a subgroup if and only if H is non-empty and X and Y are the element of a H, then X, Y inverse is also the element of H. So there is a 2 conditions we have to just say that is satisfying. So one is H should be the non-empty, another is if X and Y are 2 elements are the element of this set H, then we have to show that X, Y inverse is also the member of this same set H. So let us begin with the proof. One way is again very trivial. We have to just say that if H is a subgroup, then clearly if H is a subgroup of a G, then H at least identity element is the belong to the H. So clearly H is non-empty. And if X is the element of a we have to just say that Y is the element of a H, then Y inverse is also the element of H because H is a subgroup. So if H is a subgroup and we have to take X is the element of H and Y inverse is also the element of H, then we can say that simply is X, Y inverse is also the element of H by the closeness of a property of this. So if it is a subgroup, then these 2 properties are trivially, then H is, we have to just say that X is the element of H, Y is the element of H, then Y inverse is also the element of H since H contains the inverses. Since X is the element of H and Y inverse is the element of H, the product is X, Y inverse is also element because H is a closed. So thus the condition A and B are satisfied in this case. So we have to prove the one way. Another way we have to just say that if these 2 conditions, suppose conversely the condition A and condition B holds for H. Now we have to show that with these 2 conditions, this H satisfy all the properties of a group, yani the identity should be exists there, and it is a closed, it is inverse of each element is exists, and because G is associative, then H is automatically associative. So we have to satisfy the 3 conditions. One is identity should be there, inverse should be there, and it is a closed in this case. So let at least one X belongs to the H, and then the condition B is saying that we have a condition B at least one X is the element of H, then we have to say that X is the element of H. Then we have to say that this condition is saying that X inverse is the element of H and X inverse is equal to identity. So identity is the element of H. So we can clearly say that if at least one element belongs to the H, because H is a non-empty, we have to show that so at least A and B are satisfied. So H is a non-empty. If H is non-empty means there is at least one element is belongs to H. If X is the one of the element of this H, then X by the condition B is saying that if X is the element of H, Y is the element of X, Y. So X the element of X is the element of H, then X inverse is also the element of H. If X inverse are the element of H, then we can say that as identity. So identity should be belong to the H. So at least identity is the element of H. Now next we have to show that the inverse with at least for any arbitrary A belongs to the H and E is the element of H and A is the element of H. So we can say that if E is the element of H and A is the element of H, so he's saying that E A inverse is the element of H. If E A inverse is the element of H, then A inverse is also the element of H. We already show that the identity element in H in this case. So for any arbitrary A, it belongs to the H and identity also we have to show that element of H. So by the again condition 2, A inverse is also the element of H. Now so H contains the inverse, so that is we have proved the 2 properties. Identity element is there, H contains the inverse also there. Now we have to show that the closeness, so with the closure property So let X is the element of H and Y is the element of H. Since H contains inverses, so Y inverses also belongs to the H, but X is the element of H and Y inverse is the element of H. So X, by the condition B, we can say that Y inverse, the inverse is the element of H, and now we have to know the property is A inverse to inverse is equal to A. Using this, X, Y inverse ka inverse is equal to Y. So X and Y are the element of this. So we have to take X and Y are the element of H, that X, Y also belong to the H. Hence H is a closed, and therefore H is a subgroup of a G by this thing. So we have to prove that, means there is we have to just say that if a set any subset H is a non-empty, and if X, Y is the element belongs to the H, then X, Y inverse is also belong to the H, then we say that this is simply is a subgroup of this group G. I just say before move to the very clearly some notations point of view, it is very important to realize that if the group is written as a addition, then the condition of this X, Y, X inverse, X, Y inverse of H becomes X plus Y minus X, X minus H, because we have to just saying that X, Y. So under the binary operation, if we take a operation is addition, then in this case we have X, Y is simply X plus Y, X inverse means minus X, and this X, Y inverse X minus Y is there. So we have to just an example, let if n is greater than 0, nz can be written as a ns, all the elements, and s is the element of a set of integer. And this we have to try to prove that this nz is a subgroup. We can say that nz, so if nz can be written into the identity of a z is a 0 additive identity in this, this is a group under addition. Z is identity 0, and then you know that 0 can be written in the form of n into 0, and n is for n is the element of a z. So this is the element of a s is the element of a z. So this is n0 can be written as the element of a nz. So we show that at least additive identity belongs to this set. So this means clearly we say that this is a non-empty. So clearly nz we have to taking this is clearly is a non-empty set. Now by the previous theorem we have to show that x and y are the element of this nz, then we have to show that under addition x minus y is also belongs to the this set. So if x and y are the element of nz, then x can be written in the form of ns, and y is the element of some nk, and s and k are the some integers. Then we have to show that x minus y, so this means x or x plus y. So x plus y can be written in the form of a, we have a this by this n times n s plus k. S and k are the integer, then sum of this is also integer. This means this n is belongs to the nz, and if it is belong to the nz, and also if we had write as a minus x means we have to just say that writing the n into minus s is the element of a z, minus s also the element of z. This whole thing is also belongs to the z into this form. So hence nz is a subgroup. By the theorem we have to say into this theorem, we have x, y is the element of this, x and y are the element of this, then x, y inverse is also belongs to the h. By this theorem we can easily say that this is clearly we have to, and minus x is there. So we can prove this nz is a subgroup of a z, or you can say that x minus y is also the belong to the h. So minus x into this form, so x is equal to this form, and minus minus k, so x s minus k is again some integer. So we have to prove into this form is there. The next criteria is quite interesting. It's obvious reduce the number of things that is one need to check, but it only work for a finite subset of a group. So if we have a group is a finite, This criteria is reduced to one like this way. If H is a finite non-empty subset of a group G, then H is a subgroup of G if and only if H is closed. We have no need of all these things. We have to just say that if we have a finite subset of a group G, then H is a subgroup of G if and only if H is a closed. So, is only the closeness properties hold if we have a H is a finite subset of this thing. So, let us try to prove this theorem. If H is a subgroup, then obviously H is a closed by the hypothesis because the condition is. So, that means one way is very trivial. If H is a subgroup, then H is a closed. So, this is one way is proof is very trivial. Now, we have to prove the other hand, assuming that H is a closed. And now, if H is a closed, then we have to show that H is a subgroup, means it satisfies all the properties of a group is there. To verify that identity belongs to H, and that for every H belongs to the H and H inverse is also belong, because H is a closed, if H is the element of a H and every H is the element of H and H inverse also is also belongs to the H. We need to verify E belongs to the H and every H and inverse also as well is there. So, we have to try to prove first identities belong to the H and H is the element, H inverse is also belong to H. If we prove these two properties, then by use the theorem we can say that previous theorem we can say that this is a subgroup of this thing. So, let us try, let E is a subgroup. So, if H has a only identity element, that is a trivial, assume that H is a trivial. So, we can say that assume H is non-trivial. So, we can say that if only the identity element in a set G, then this proof is nothing. We have a trivially, this is a subgroup, and then finish. We have to assuming that G, this H is a non-trivial. That means H is a non-trivial means H contains an element H distinct from identity. So, H contains a element H and different from identity. So, if it is, we have to assuming that H is a non-trivial. If non-trivial means there is a at least one element I accept identity. If we have a just identity element, that is a trivial is a subgroup. We assuming that H is a non-trivial means H contains an element H, for example, is distinct from the identity element. And now since H is a closed, so if H is the element of a H and H is a closed, then H square is equal to H into H is also the element of H, and similarly H3 is equal to H into H into H is also the element of H. In this case, we have to just say that H is a closed, so the elements of H, H square, H cube and so on all are in H by the closeness of this. So, we have to just say H is distinct from H identity element. So, H is the element of H, then we have H square. H square means H into H, this is the by the closeness is also belongs to the H, X cube, X square into H by the closeness is also this is the member of H. So, in this way this H, H square, H cube all are the elements of H. Now, we have a given condition, this H is a finite, this is condition we have a given. So, we have a given condition that H is a finite means they cannot all distinct. So, we have to going into such a way at such states, some certain state, suppose Hn is there, after certain state this is equal to Hn is there. So, that means we can say simply that they all are not distinct, means at some point they are the same in this thing. So, we have to just say that let there exists a positive integer m and m greater than equal to n such that h to the power m is equal to h to the power n. Means at some positive integer m, then this power h to the power m is the same as the h to the power n. If h to the power m is h to the power n, and then we can say that h to the power m minus n is equal to identity. So, now we have a possibility, we can say that if h to the power m minus n minus 1 is equal to A inverse, so this means h is equal to n inverse H inverse is equal to E, so E is equal to identity. So we have to just say that possibility is there if m minus n is equal to 1, if this quantity m minus n is equal to 1, then H is equal to, we have a identity. So F is an identity, if H is the identity, in this case we have a H inverse is the is, so we have to write this H is the, this means we have a H and then we have a inverse of a this is equal to identity into inverse, this is equal to H inverse. So this means H inverse is equal to identity, and this identity is already is an element of H, then we can show that H inverse is the element of a H is there. Now suppose m minus n is greater than 1. If m minus n is greater than equal to 1, greater than, strictly greater than 1, equal to 1 is we have to done already, then this can be written as a h to the power m minus n minus 1, then this can be also written as h to the power m minus n minus 1 h, and now this is nothing but is equal to, is written as h to the power m minus 1. So this is, we can write into this form. So E is equal to h to the power m minus 1, we have to just, this can be written in the form of h into this form or into this form. Now that is we can say that h to the power m minus 1 is equal to h inverse, because we have to just say that this this thing is equal to identity, so we have to just say the multiply the inverse, because already h inverse is the element of h. So this h inverse is equal to h inverse, but you just see that this m minus n minus 1 is a positive integer. That means we have to h to the power m minus n minus 1 is the element of a h, and so h inverse is the element of a h2. So because h is a closed by the hypothesis, it is subgroup by the theorem is equal to this. So we have to prove that h identity is there, h inverse is also is there, and then we have to prove that because h is closed by the hypothesis, then it is a group by the this theorem. We just say that by this theorem non-empty, we have to just say that already finite set and these two conditions are hold. So in this case we can say that this clearly, if we have a group is a finite, so we can say that clearly reduce the only closeness we have to taking into this form. So we have to say that if a H is a finite subset of a group G, then clearly we say that H is a closed, is enough to show that is closed and is a subgroup. For example, we have to taking this H is equal to K into Zn. You know the Zn is a finite group under addition. This Zn is a group under addition modulo n. So n and k, H we can assuming that k into x is the element of any z. So we take certainly H is a non-empty, because we have a under addition is a 0, so 0 can be written as a some k into 0, and 0 is the this is the element of a H is there. So H is the clearly identity element is belongs to there, so H certainly is non-empty. Now we take a two elements x kx under addition modulo n ky. This can be written as a kx under ky can be written k times of x under addition modulo y, and x and y are the integers. So this is simply write does this form. So therefore H is this is the element again belongs to the H, and this is belongs to the set of Z, or the whole set is belongs to the Z H, and if it is belongs to the H, this means we can say that this is kx under addition modulo n, ky is also the element of a H. So therefore H is closed under the addition in Zn, and so Zn is a finite, and theorem this just say that H is a subgroup of a G is there. So now we have to prove this clearly by this result, that if we have a H is a finite subset of a group G, then set of if it is enough to show that only the closeness, if it is no. But if we take as infinite, this maybe the closeness is not a true, because we take a, suppose for example, if we take a set of integer under addition is a group, and we take a some infinite subset n, and set of natural number under addition, set of natural number under addition is itself is a subset of this and closed, but you can see set of a natural number under addition is not a group, because the identity element is does not exist. So this is theorem is applicable only if you have a finite set, subset of a group G, and if it is closed, then we have to say that is a subgroup is there. So I think I have to stop today lectures here. I discuss the property today's define the subgroups and some criteria how to find a subgroups and definition of a subgroups. In the next class we have to continue some more properties of a subgroup. So that means we have to find intersection and of subgroups, union, and we have to define the some other structures of the subgroup. Thank you for today's lecture. Thank you very much.